Well, welcome back, ladies and gentlemen. Today we're going to talk about continuity and what that looks like in a graph. This was a primer question that I asked you to give some thought prior to entering today. Hopefully you've got an idea of what it means to be continuous. And when I say continuous, I don't mean something that's super special like a math word. Well, it is a math word, but you should be able to think about it. What does it mean for a function to be continuous just from an English perspective? What does that look like? And you might say, well, if a function is continuous, it probably looks, I don't know, the picture I always have in my head is something like this. It looks kind of curvy and wavy, and it travels on in both directions. But the point is, I was able to draw that without my pencil coming up. And what does continuity not look like? Well, we've had a few examples. We've had situations where we had like a jump discontinuity like this. We've had a situation where we might approach some unbound behavior, so maybe something like that. There's a few situations where maybe there's a point that's been removed or displaced, so maybe something like that, or something maybe where the hole is still there, but the point has been relocated above or below it. And those are all great examples of what discontinuity looks like. Basically, from a visual or an artistic perspective, in order to draw a graph that is not continuous, you need to pick up your pencil off the paper in order to complete the graph. So I have a quick summary of what it looks like visually, and I have one additional example that we may not have thought of as being not continuous. So continuity, the picture that always appears in a textbook is this nice little cubic function with two local extrema, a maximum and a minimum. And this is a function that you can draw in one pencil stroke, maybe excluding the highlighted point. The point here that they've shown, this little dot right here, does not require you to pick up the pencil. They're just highlighting a specific x value for it. These were the different types of discontinuities that we just drew on the other screen. We got a jump discontinuity, we got a removable discontinuity. We actually have two types, one where the function is defined and one where the function is undefined. So there's two different types of those. We're going to call this type of discontinuity, sometimes it's called an essential discontinuity, sometimes it's called an infinite discontinuity. Other times they just say it's not continuous because there's a vertical asymptote there. But I wanted you to note that there are two versions of this, one where the function is traveling both directions, and one where the function is traveling in the same direction. And the difference being is that here we're actually going to use this symbol. If we're asked a limit question, we're going to use that symbol to demonstrate unbound behavior, whereas this one we're going to say DNE. Just to be clear, remember that both limits do not exist, but this one we can be a little bit more specific. The last one that we didn't actually draw in the previous screen is this one, the oscillating discontinuity. And this is the function sine of 1 over x, and this is always an example of this type of discontinuity. This is where something oscillates infinitely more frequently as you approach a certain value. So as we approach an x value of 0 here, this is oscillating more and more and more, and to a point where there's actually also an undefined function value right at 0 as well. Altogether, these are the types of discontinuities that we're going to experience during this year. I don't think there's one that we haven't talked about yet on this screen that we're going to experience later. But what we're going to spend time with today is defining exactly in a mathematical context what continuity is. I have one more little note here, and that is this function right here. This little caveat right there. If we look at a rational function or something with an asymptote that's kind of built into the function, the asymptote is part of that function just as a parent. We say that a function like this is continuous on its domain, but understand that the domain itself has some restrictions. So other than the x value of 0, this function is continuous everywhere else. Then the next step is to say, well, how do we define something mathematically now that we know how to do it visually? And if we take a look at this picture here, basically whatever the function looks like, it's basically, we could draw a curvy, and let's say that this is the point in question. Maybe it's easier to define continuity at a point rather than along the whole way. And what's true about this? Well, I was able to draw this one single line, and it encompassed all the area that I needed to. You'll notice that as we approach, say, this point in question, whatever it is, I'm going to draw an axis like this. Sure, why not? As we approach this point along the curve, notice that the limit exists. So if we call this point C on the x-axis here, we can say that the limit, and maybe we give this a name too, f of x. We notice that the limit of f of x as x approaches C exists. Okay? Not only that, but it appears to be a number, and that number we could define further conveniently as f of C. So instead of just saying that it exists, and we do need that, we can say that it's f of C. And that is basically the cleanest definition of continuity. You'll notice that none of these match this. Right here, the limit doesn't exist. Right here, the limit exists, but the function's value is not the same as the limit. Right here, the limit exists, but the function is not defined at that value. Right here, the limit does not exist. Right here, the limit does not exist. And right here, the limit does not exist. So all of those other cases get thwarted by this one simple statement. So officially, definition of continuity, the simplest form of this definition is simply one line. It simply states that the limit, as we approach any x value in the domain of f of x, that limit must exist, and that limit must be equivalent to the function's value at C. Okay? And there's an awful lot that is hidden in this definition. So I want you to understand that this is the simplest way of writing continuity, but in fact, when you're answering a continuity question in AP Calculus, you need to go one step further than that. In fact, you have to understand that there's hidden meaning behind each one of these statements. So, for instance, just because we put f of C in this equation, that's all well and good, but that implicates that f of C must exist. So that's one of the conditions for continuity in the expanded kind of AP definition of what continuity is. Secondly, in order for this to be in our equation, the general limit must exist, okay? It must exist in order for us to use it in an equation. And in order for that limit to exist, that means that the left-hand unit and the right-hand limit must equal the same thing. So left-hand limit has to equal the right-hand limit, and that thing must be a number. It has to be defined. It has to exist. So if it doesn't exist, like in this situation, then this condition, this second condition, fails. Okay? And finally, the last thing that we need is that we need the limit, whatever it was, the numerical value of the general limit needs to equal the function's value. That's how we eliminate situations like this as being called continuous. If we put these three things together, the limit exists, and the value of that limit is the value of the function, then we have continuity for any point C on the domain of f. Okay? Now, this is the expanded definition down here. This is the simplistic version of the definition right there. Here's what AP wants, okay? So when there's a variety of questions, especially in FRQs, where it says something like, is the function continuous at an x value of their choice? Here's the three things that you must show to prove that something is continuous. You must go through and say that f of C exists. Secondly, you have to show that the limit exists. So that might involve doing both a left-hand and a right-hand limit, and then getting a number. And then finally, you must show that these two numerical values are equal. Okay, so you have to make sure that the limit from left and right-hand side matches the value of the function at that given value. Okay, so a lot of the problems today are more conceptual than they are algebraic. Okay, so again, these are the three requirements for an AP proof that something is continuous at a point. Here's an example of the type of questions that you could be asked for any sort of continuity question. Determine the continuity status at a particular value. You could be asked to discuss the continuity. That's the way our textbook phrases it. When I say discuss the continuity, I'm expecting you to address these 3 points for that x value. Multiple choice, they're basically going to have those three conditions somewhere in the answer bank, or maybe a combination of those two, or say which of the following A and B, or B and D, or E all of the above are true at x equals 5. This is a good one. List all intervals on which f of x is continuous. So you're going to look for discontinuities and ignore them. And the other thing you might be asked to do is to fix a discontinuity. So if it's a jump, you might be asked to shift the function up or down to match. Or if it's a hole, you might be asked to fill in that hole. So you're going to see some piecewise functions in here. All right, speaking of, let's look at this problem. This problem asks, is f of x continuous at x equals -1 or x equals 3. Justify your answers, list all intervals on which, and then list all intervals on which f of x is continuous. So let's deal with at x equals -1 first. So I'm gonna, this is a long problem because I have to discuss each of those three things. So firstly, just by looking at it, do you think that that is continuous or not continuous? Well, I would have to pick up my pencil to draw that region. So I'm going to say it is not continuous. And I can say because. All right, now this is where we have to find one of those three statements, okay? And we have to say which one fails. Well, the limit exists, the function exists, the limit exists, but that limit is not equal to the function's value. So see that the limit is a different y value than what the function's value actually is. So we can say the limit as x approaches -1 of f of x is not equal to f of -1. That's our justification right there. Okay? Let's talk about 3. Okay? So at x equals 3, well, 3 would be right here. Trace that down. Looks like the function goes right through an x value or a y value of -3. I'm going to go out on a limb and say that's continuous. I could draw that without lifting up my pencil or pen. Okay, so that means that I have to show that 1, we've got f of 3 equals -3. It exists. F of 1 or f of 3 exists. So I've hit that bullet point. Number 2, I got to show that the limit of f of x as x approaches 3 equals -3. Check. Just look at the graph right there. Okay. And then condition number 3 is that these two match each other. So we can say that, write it out, just in doubt, write it out. So limit of f of x as x approaches 3 equals f of 3, and you could even triplicate it here, equals the height of -3. Basically, that one line does it all, but AP wants you to step through each of those steps. Lastly, we are asked for what x values is f of x continuous on. So this is again asking for a domain on which, whenever it asks for an interval, it's asking for domain values on which it is continuous. So assuming that there are arrows here, and they would be drawn on an AP exam, we will assume that we've gone from -infinity all the way up to an x value of -1. It is not continuous at 1, as we just proved above. And then it looks like it's continuous up until an x value of 4. So I'm going to exclude the 1, but I'm going to pick it up right afterwards. I'm not going to include 4, and then I'm going to go from 4 to infinity, as there are no more holes or gaps in the function. There we go. There's a complete list of intervals on which that is continuous. Next up, we can do one algebraically. So this one doesn't have a graph. It relies on your ability to identify what types of discontinuities are present on a graph like this. So whenever you see polynomials, especially trinomials, you want to try to factor them. So let's see if we can do that, see if anything cancels out and what that would mean. This is a review of pre-calc if you haven't figured that out yet. So let's see. We got an x minus 3 and an x plus 1. Now, this information right here implies that there are discontinuities at x equals -1 and at x equals 3. So that means that my answer to both of these questions is that it's not continuous. But I have to understand which type of discontinuity are we dealing with. Whenever you see something that matches up on top, f of x is going to have a removable discontinuity right there. So we have f of x has a removable discontinuity at x equals 3. That means that f of 3 does not exist. Therefore, condition 1, number 1 fails, and f of x is not continuous. There we go. That's what, I mean, it's a lot of writing. It's a lot of things to think about. Okay. Now, the remainder of this function after it's been simplified is 1 over x plus 1. So we have 1 over x plus 1, and that means that, again, we have a discontinuity or an undefined, let's not do that. Let's say that f of negative 1 is undefined. That means condition 1 fails. And f of x is not continuous at x equals 1. Or is it 1 or negative 1? It's negative 1, sorry. There we go. And just for your information, this graph, when we graphed it, we'll have a vertical asymptote at negative 1, and we will have a hole somewhere at an x value of 3. So there will be a hole in the graph here, and we'll either have something that looks like this sort of thing going along like that. So I might have the signage wrong on that, but real roughly, we'll have a hole at 3 and a vertical asymptote at negative 1 just off of that. So since the function does not exist at either value, that's the biggest reason that it is not continuous at either value. Next up, we have a piecewise function. Okay, so we have a function that's defined in 3 different ways. We do not have a graph of it. Okay, so basically at negative 1 and 3, you'll notice that those are the breakpoints for the function. So we have to make sure that these things line up. So we've got some sort of parabola, and we're hoping that it lines up with a linear function that we're then hoping lines up with another linear function like that. I have no idea if this is the way the graph looks or if I'm just hoping that it is. So basically, we want to figure out, this is at an x value. If I trace that down to an axis, this is at negative 1. This is at 3, even though I didn't draw that very proportionally, but you get the idea. Basically, we have to make sure that that value, that corner lines up. Easiest way to do that is to figure out what f of negative 1 is, and that equals negative 1 squared minus 4 times negative 1 plus 3. And we get 8 by doing that. Then we also, so that was using the parabola. Now let's think about the limit as x approaches negative 1 from the positive side. Well, then I'm going to use this function, 2x plus 10. And so to evaluate that limit, now because basically this is me checking the right hand or the left hand limit, left side. This is me checking the right hand side over here. Okay, so then we just plug in that number again, 2 times negative 1 plus 10, we also equal 8. So therefore, we should probably, since we're doing this officially, we better do a limit statement. So then we can say that the limit exists and is equal to the function's value. So negative 1 from the left-hand side is of x squared minus 4x. So this time I'm using the parabola, but I'm using it as a limit statement. And we just figured out that that is also 8. So we can say that since the limit of f of x as x approaches negative 1 is equal to f of negative 1, f of x is continuous at x equals negative 1. Okay, so that's how you do a continuity proof. The other one that we were asked to do was 3. So we want to look at, again, basically left-hand limit, right-hand limit, and the function's value itself. So might as well start with the limits, just stay consistent. X approaches 3 from the left-hand side, limit of x as x approaches 3 from the right-hand side. And we also want to figure out what is the actual function's value. And hopefully these things all match. Okay, so we're going to do this. And since we are coming from the left, we're going to use the 2x plus 10. So we have 2, and we're just going to do direct substitution here. Okay. And then the right-hand side, we got 13 minus 3. That's equal to 10. And right here we can already say, we don't even need to know this. So since the limit as x approaches 3 of f of x does not exist because of a jump discontinuity. One side's going to 16, one side's going to 10. So that means that this graph was actually looking a little bit something like this. Okay, so that's the situation we got going on. We can say that f of x is not continuous. Not continuous at x equals 3. As soon as one of the three conditions fail, we can say it's not continuous at that because of that and move on. All right, let's move on to this one. This is one where we have to fix it, okay? For what values of c, if any, is g continuous at x equals 3? So in other words, we want to figure out the value of c for which that basically makes these two functions line up, which means that we want c squared minus x to be equal to cx minus c. Okay? That more or less assures that the y values line up at 3, at x equals 3. Okay? Now, we need to find a value c, and there's a whole bunch of variables in here, but we do know one more piece of information. We're only concerned about when x equals 3. So we're going to go c squared minus 3 equals c times 3 minus c. And from there, it's just our ability to solve an equation. So let's see. We're going to have c squared. This would be a 2c, so minus 2c minus 3. All right, and then we can factor that. We go c, not x, minus 3, and c plus 1. So c, not x, equals 3 or negative 1. Okay, so a value, well, lots of 3's and negative 1's. This is not related to the previous problems in any way, but the values of 3 or negative 1 both work to make that function continuous. Here's our next problem. The question is g of x equal to the square root of x continuous on its domain? Justify your answer. Now, this is kind of an interesting question because the function ends right there. And if I say on its domain is numbers that include 0 up on towards infinity. So that means that I have to check the continuity at 0 in addition to all these points. Okay, so I think it's fairly obvious that the limit exists and everything is continuous there. But the one thing that we have to check here is the limit at x equals 0. But since we can't check from the left-hand side, the only thing that we need to check is from the right-hand side. So this actually makes things simpler. We just have to think about it in a weird way. As x approaches 0 from the right-hand side of the square root of x, what does that equal? Okay, and we can do that. It's approaching a value of 0. And we can also say that f of 0 would equal the square root of 0, which equals 0. And we also note that f of 0 exists. All right, so there we go. We got condition 1. Condition 2 is that, now this one got simplified because we only had to check one side of the limit. We only had to check the right-hand side because that's the only side that's in the domain of the square root of x. And then 3, that these two equal each other, and that's condition 3. Therefore, f of x is continuous, or is g of x, isn't it? Sorry. Well, this whole thing, replace all my f's with g's, is continuous for all of its domain. And really, it was only the endpoint that was a problem, okay? How do you check continuity at a point? Basically just like what we did. You only have to check half of the limit, the right-hand side limit or the left-hand side limit. So here is some definitions of continuity at endpoints. If you care to jot it down, you may, but just know that it's a slight variation on the definition of continuity as a whole. You just only have to check one side of the limit rather than both. All right, and then lastly, I'll close with one type of question, which is, what types of functions are always continuous? There are families of functions that are always continuous. Pause the video and see if you can list a couple types of functions that are always continuous. AP recognizes these families as being always continuous, and I hope some of these are obvious. Power functions, that would be like x to the 4th, x to the 10th, something like that. And polynomial functions, pretty obvious that they're always going to be smooth, curvy things with no holes or gaps or vertical asymptotes or anything funky like that. Trig functions, sine and cosine, those are just waves. They don't have any holes or gaps anywhere, so that's no problem. Exponential functions, again, no holes or gaps or anything like that. There are a few functions that we say are continuous on their domain, and that's because their domains have limitations. So they are rationals, where you might get, we did an example up above where we had a whole and an essential discontinuity. Logarithmic functions, which are only, their domain is greater than 0 in general, the parent functions anyways, and the other trig functions that have holes at pi/2 increments or pi increments will all be considered continuous on their domain because we just ignore the values that aren't in the domain. That's all I have for you today. I'll see you next time.